85% of the matter in the universe either doesn't exist or we're fundamentally wrong about how gravity works. Physicists have spent 50 years trying to figure out which, and they still don't know. By the end of this video, you'll understand why both possibilities are mathematically sound and why neither one has won. This is the state of modern cosmology, two well-motivated theories, both with fatal flaws. The problem didn't arrive from philosophy or speculation. It arrived from observation. In 1975, an astronomer named Vera Rubin was studying the rotation of galaxies. Specifically, how fast stars orbit around galactic centers. If you've ever thought about our solar system, you know that planets closer to the sun move faster than planets farther out. Mercury orbits in 88 days. Neptune takes 165 years. The farther from the sun, the slower the orbit. The mathematics here is straightforward. Orbital velocity depends on the mass you're orbiting divided by your distance from it. The relationship is so reliable that Isaac Newton worked it out 3 centuries ago. But when Rubin pointed her telescopes at galaxies far beyond our own, something was wrong. Stars at the outer edges of galaxies moved at almost the same speed as stars near the center. Not faster, not slower. Almost constant. This is wrong. According to Newton and Einstein both, the outer stars should be moving slower, much slower. The orbital velocity should drop with distance. Instead, it was flat. The curves were flat across hundreds of galaxies. Same pattern, repeated consistently, as if nature was following a single rule that shouldn't exist. Now, watch what happens when you follow the mathematics. If visible stars and gas account for the only gravity in a galaxy, the orbital velocity should decrease with distance. The calculation is simple, but the observations showed flat curves. That gap, that mathematical impossibility, meant one thing. There was mass in those galaxies that we couldn't see. A lot of it. In fact, when you run the numbers, the invisible mass needed to hold those galaxies together was about 5 times the mass of all the visible stars combined. So astronomers faced a choice. Either stars were held in place by matter that didn't emit light, or gravity itself worked differently than they'd been taught. That choice created 2 competing frameworks. One is called the dark matter hypothesis. The other is called MOND, modified Newtonian Dynamics. And here's where the story gets intellectually rich. Both of them work. Both of them explain the rotation curves. Both of them fail on different observations. Neither one has ever been proven. This is where we still are in 2025. Before we look at what each theory proposes, you need to see the 3 observational facts that both theories must satisfy. These aren't guesses. These are measured, confirmed, consistent measurements across decades of telescopes and increasingly sophisticated instruments. The first piece of evidence is what we just discussed, galaxy rotation curves. Vera Rubin's original data from the 1970s. But the work didn't stop there. In 2016, Stacy McGaugh and colleagues at Case Western University compiled what's called the SPARC database. SPARC contains detailed rotation curve measurements for 175 galaxies, ranging from small dwarf galaxies to massive spirals like the Andromeda Galaxy. The curves are extraordinarily consistent. Not perfectly flat, there are variations, but flat enough that they cannot be explained by visible matter alone. This is not controversial. Every cosmologist agrees on this data. The interpretation is what's contested. The second piece of evidence is gravitational lensing. Here's how it works. Space is curved by mass. Light follows straight paths through space, but curved space makes those paths bend. Einstein predicted this in 1911. We first observed it during a solar eclipse in 1919, when starlight near the sun appeared to shift position slightly. The amount of bending depends on the total mass between you and the light source. So when we look at distant galaxies and see their light bent by massive structures in the foreground, we can calculate the total mass of whatever is doing the bending. And here's what we find. The mass needed to produce the observed lensing is about 5 times the mass of visible matter. Same factor as the rotation curves. Same problem. But there's one lensing observation that stands out above all others. It's from 2006. 2 galaxy clusters collided. They're called the Bullet Cluster, named 1E0657-56 by astronomers. What happened was this. 2 massive clusters of galaxies were moving at high speed on a collision course. When they hit the normal matter, the stars, the gas, the atoms interacted, gas clouds collided with each other, friction slowed them down, they got hot. X-ray telescopes detected them at collision center, radiating energy as they decelerated. But gravity doesn't get slowed by friction. The gravitational center of mass, where the lensing shows the total mass to be, is displaced from where the hot gas is. It's forward of the gas, separated by thousands of light years. This is the smoking gun observation for dark matter. If gravity were simply modified the way MOND proposes, the gravitational center and the visible matter center should move together. They don't. They're separated. This single observation has convinced most physicists that dark matter is real. It's the reason MOND, despite its elegance, has fallen out of favor. The third piece of evidence comes from a completely different direction: the cosmic microwave background, the afterglow of the Big Bang. The universe cooled from nearly infinite temperature to a state where atoms formed. At that moment, about 380,000 years after the Big Bang, light decoupled from matter and traveled freely. We detect that light today. It's in the microwave part of the electromagnetic spectrum, but it's not uniform. There are tiny temperature fluctuations, about 1 part in 100,000. These fluctuations follow a specific mathematical pattern. They have peaks and troughs at particular angles in the sky. In 2018, the Planck Space Telescope released its final measurements. The pattern of these temperature fluctuations depends precisely on the amount of dark matter in the universe. More dark matter shifts the peaks. Less dark matter shifts them the other direction. The Planck data shows that dark matter makes up about 27% of the universe's mass-energy content. Normal matter, atoms, stars, makes up about 5%. The rest is dark energy, which is another puzzle entirely. But the point is this: the CMB power spectrum is exquisitely sensitive to dark matter. It constrains the amount to within tight bounds. And here's where it gets interesting. MOND cannot explain the CMB power spectrum without adding dark matter anyway. So even the alternative theory concedes that most of the matter in the universe is invisible. The dark matter hypothesis is straightforward. 85% of the matter in the universe is a particle or collection of particles that does not interact with light. It doesn't emit it, doesn't absorb it, doesn't reflect it. It only gravitates. It is invisible by definition. We know it's there because we can measure its gravitational effects. Now, physicists have proposed many candidates for what dark matter actually is. The leading candidates were WIMPs, weakly interacting massive particles. WIMPs would be particles with mass in the range of 100 to 1,000 gigaelectron volts. They would interact via the weak nuclear force. They fit naturally into supersymmetric extensions of the Standard Model, where every known particle has a heavier partner. For decades, WIMPs were the favorite. Physicists built enormous underground detectors to search for them. The XENON collaboration filled massive chambers with liquid xenon, shielded underground to block cosmic rays. Thousands of kilograms of xenon waiting for a WIMP to collide with a nucleus. The sensitivity was extraordinary. If WIMPs were as abundant as predicted, the detectors should have seen them. They didn't. Year after year, zero detections. Xenon, 1T, Lux, Super CDMS all came up empty. So attention shifted. Other candidates emerged. Axions became popular. Axions are hypothetical particles much lighter than WIMPs, perhaps 1/1,000,000th of an electron volt. They were proposed originally to solve a completely different problem in particle physics, the strong CP violation problem. But they also work as dark matter candidates. The advantage is that no one expected WIMPs to be this hard to detect. Axions are genuinely elusive by design. Experimental techniques to search for them are still in their infancy. If dark matter is axions, we haven't detected them yet simply because we haven't developed the right tools. Another candidate is primordial black holes, formed in the early universe from density fluctuations before galaxies even existed. They would require no exotic physics. They're just black holes. The problem is that some mass ranges for primordial black holes have been ruled out by gravitational lensing observations. Other mass ranges remain possible. Sterile neutrinos are another option, neutrinos that only interact via gravity, completely decoupled from the electromagnetic and weak forces. They would be nearly impossible to detect directly. They fit mathematically. but there's no compelling evidence for them. Here's the honest assessment. Dark matter is probably real. The rotation curves, the lensing, the CMB all point to large amounts of invisible matter. But after decades of searching, we have not detected the particle. Not once. We've ruled out enormous ranges of parameter space, but we haven't found the thing itself. That gap between theory and experiment is significant. It's the reason physicists remain genuinely uncertain, despite the consensus favoring dark matter. There's another problem, more subtle. When you run cosmological simulations to see if dark matter can explain the structure of the universe, you get predictions. The simulations show how many small galaxies should exist compared to large ones, how galaxies should cluster. The predictions don't quite match the observations. There are fewer small galaxies than predicted, fewer satellite galaxies around large ones than the simulations suggest. This is called the dwarf galaxy problem. It might be resolvable, perhaps our simulations are incomplete, or our understanding of how galaxies form is wrong, but it's a persistent discrepancy. And there's the core cusp problem. In the centers of galaxies, dark matter simulations predict dense cores, but observations show diverse structures. Some galaxies have cusps, some have flat cores, some have something in between. No unified picture. Dark matter doesn't automatically explain why galaxy centers look the way they do. These aren't fatal flaws for dark matter. They're loose ends, but they're significant enough that physicists should maintain intellectual humility. The theory works, but imperfectly. Now, let's look at the alternative. In 1983, an Israeli physicist named Mordechai Milgrom proposed something radical. Instead of invisible matter, change gravity itself. At very low accelerations, gravity doesn't follow Newton's law. The force isn't simply proportional to mass divided by distance squared. Instead, at low accelerations, below a certain threshold, gravity becomes stronger relative to distance. Here's the mathematical core. Normally, acceleration equals force divided by mass, A equals F over m. But Milgrom proposed that at low accelerations below about 1.2 times 10 to the minus 10 meters per second squared, the formula changes. It becomes F equals m times a zero times mu of A over a zero, where a zero is that threshold acceleration and mu is a function that behaves like 1 over x for small x. In practice, this means that in the weak gravity regime, gravity becomes stronger than Newtonian gravity predicts. Why would this matter? Because in the weak gravity regime, orbital velocity around a galaxy becomes approximately constant with distance. Flat rotation curves fall out naturally. You don't need to add invisible matter, you just need gravity to behave differently in the weak field. This is elegant. A single parameter, a zero. The transition acceleration works across all galaxies. You don't need to carefully adjust dark matter density profiles for each individual galaxy the way you do with the dark matter hypothesis. MOND makes predictions without fitting. This is mathematically satisfying, and it works. Stacy McGaw's Spark database, the same one that showed rotation curves are flat, also showed that MOND predictions match remarkably well. Better, in fact, than dark matter predictions in many cases. When physicists from a 2016 paper reviewed the data, they titled their result, "One Law to Rule Them All." The universality of MOND, how a single modified gravity law captures rotation curves across galaxies of wildly different sizes and masses, is genuinely impressive. But MOND faces a problem that dark matter doesn't. It's non-relativistic. Modern physics is built on relativity. You can't have a theory of gravity that ignores Einstein. So in 2004, Jacob Bekenstein developed a relativistic version called TeVS, tensor vector scalar gravity. It modifies Einstein's equations themselves. It reduces to MOND in the non-relativistic limit, but extends consistently into relativistic regimes. It's mathematically complex, but coherent. The problem is that TeVS faces its own challenges. Gravitational waves are a prediction of Einstein's theory. If you modify Einstein's equations to get MOND-like behavior, what do gravitational waves look like in TeVS? The mathematics gets complicated. Other relativistic extensions of MOND, proposals by different physicists, face different obstacles. There's no fully satisfactory relativistic version of MOND that physicists universally accept. But the real problem for MOND is the bullet cluster. Remember, when those two galaxy clusters collided, the visible matter got slowed by friction. It piled up at the collision center. But the gravitational center, where lensing points to the bulk of the matter, is displaced forward from the hot gas. MOND predicts that gravity should follow the matter distribution. If most matter is in the visible gas, gravity should be centered on the gas. But it isn't. The gravitational signature is separated from the baryonic matter. This separation is massive evidence for dark matter existing as a separate component. It's nearly impossible for MOND to explain. You could propose that MOND has exceptions, or that relativistic effects matter more than anyone realized, but these are ad hoc additions. They weaken the elegance that made MOND attractive in the first place. And there's the CMB problem. The cosmic microwave background power spectrum depends sensitively on dark matter. MOND alone cannot produce the observed peaks and troughs, not even close. So even MOND advocates have had to add dark matter into their models. But if you're adding dark matter anyway, why not just accept the dark matter hypothesis from the start? Why bother with MOND? Here's what we're left with. Two theories. Both explain some observations perfectly. Both fail on others, and neither has been proven. Dark matter is statistically favored by most physicists. The consensus leans that way. But consensus in physics is not the same as proof. Dark matter is undetected. After more than 40 years of direct detection experiments, we have not captured a single dark matter particle. We've ruled out enormous ranges of what it could be, but we haven't found it. That absence, that persistent gap between theory and experiment is significant. Meanwhile, MOND remains mathematically elegant. It explains rotation curves without exotic particles. It makes surprising predictions about scaling relations between galaxy properties that actually hold up when you test them. Some physicists argue it's been unfairly dismissed because of the bullet cluster. They work on variations and extensions. They're a minority, but they're real physicists doing legitimate work. The bullet cluster is the strongest evidence against MOND, but there's a philosophical position you could take. Yes, the bullet cluster is puzzling for MOND, but maybe it requires a deeper understanding of relativistic gravity in extreme regimes. Maybe our intuitions about how gravity should behave are wrong in the same way that classical physics intuitions failed in quantum mechanics. This is not a crazy position. It's speculative, but not irrational. But the CMB is harder to defend against. The power spectrum is so sensitive to dark matter density and so well measured by Planck that it's hard to see how MOND avoids requiring dark matter. And if you require dark matter anyway, MOND loses its core philosophical appeal, that you don't need to add invisible matter. Here's the honest state. Physicists lean toward dark matter. The evidence suggests it's probably real, but nothing has been proven. Direct detection remains zero. The galaxy formation simulations have problems. The core cusp discrepancies persist. So even the leading theory has unresolved issues. You might think this is frustrating. A century and a half after Einstein, with all our telescopes and detectors, we still don't know the composition of 85% of the matter in the universe. But this is how science actually works. Two competing frameworks, both with merits and flaws, and no consensus. This is not failure, this is the state of knowledge. It's honest, it's accurate, and it's where we remain. One more possibility exists, though it's speculative. Perhaps dark matter is real, maybe 30 or 40% of what we need, and gravity is also modified at very low accelerations enough to account for the rest. A hybrid approach. The mathematics could work. Neither dark matter advocates nor MOND advocates have ruled it out, but there's no strong evidence pushing physicists toward this hybrid view. So most work proceeds on one track or the other. What does it mean that we don't know? That despite everything we've measured and calculated, 85% of the matter in the universe remains a mystery? It means the universe is stranger than our intuitions allow. It means gravity, even after Einstein, might have properties we don't yet understand. It means the particles we know about electrons, quarks, photons are a tiny fraction of what exists. Or it means gravity itself needs revision in regimes we haven't fully explored. This is not unusual in physics history. Dark matter would be invisible and seemed absurd when first proposed. Then observations accumulated. Gravity is mysterious and seems counterintuitive at relativistic speeds. Then experiments confirmed Einstein's predictions. The pattern repeats. Nature reveals strangeness. Our theories adjust. You began this video hearing that 85% of the matter in the universe might not exist, or that everything you know about gravity might be wrong. By now you understand something deeper. We have measured the gravitational effects of unseen matter or modified gravity thoroughly. We have two mathematically coherent frameworks that explain large swaths of observation. Both fail somewhere. Neither has been proven. The scientific honesty here is important. In a field where there are only two major competing theories about something fundamental, and both have significant problems, it's not legitimate to declare one winner. It's legitimate to say one is more popular, more developed, more supported by most observations. But popular is not proven. Here's what matters. The universe's structure is determined by something we've only begun to understand. Whether it's dark matter or modified gravity or something we haven't imagined yet, the answer will reshape physics. It will tell us something fundamental about how reality works at the largest scales. And we don't know yet. That uncertainty, that intellectual humility, is the honest conclusion. Not dark matter exists, and we're searching for it. Not MOND is the real answer, and physicists won't listen. But something profound is wrong with our understanding. Both competing ideas capture part of the truth. Neither is complete. The answer will change everything. That is where we are. That is where modern cosmology stands in 2025. Two theories, one universe, and everything still to discover.